Welcome to my series on stochastic processes. As we'll see on the next slide, there's 12 lessons in this series. This is the first lesson on foundations, and we're going to cover random variable stochastic processes and Markov chains in this lesson. This series of lessons are based on a chapter from my book, Mathematical Vignettes, and I'll make the link to my book available in the description to this video, and the electronic version is actually free, so you may want to download that. I have a summary of the different parts of the series. We're doing part 1 right now, and there'll be a second part on foundations and transition probabilities. Then there's 2 parts on Gambler's Ruin, 2 lessons I should say, on random walks, 2 lessons on the classification of Markov chains, 2 lessons on continuous time and Poisson processes, and then the final 2 lessons are on birth, death, processes, queues, and generators. And here on the right I have the prerequisites, although I'll go over some of these, but it would be good if you're seeing them as a review rather than for the first time. So probability, including random variables, expected value, and variance, a little bit of calculus, limits, derivatives, integrals, and then difference equations. Everything that we're going to talk about in this series depends on the idea of a random variable. So I want to introduce that here. First, a little bit of notation. So we're going to be using P for probability. That's pretty typical. And then we have the notation shown here. The probability that A equals 1 equals 0.5. So that's a probability statement. It's just saying the probability of some event A equaling 1, it has 0.5 probability. A random variable assigns a number to each outcome of a process. And we'll see some examples of this, including one on the right here, which I'll get to in a second. Which number you get depends on chance. In other words, which value for the random variable. Each possible value carries a probability. So here's our example, and we'll continue this on the next slide. A simple game. We roll 2 die, or dice. Some people don't use the formal die is plural, on a $1 bet. So if the sum is odd, you win $2, and if the sum is even, you lose your dollar and you win nothing. The payout is a random variable x, so it would have either the value 2 or 0. Let's continue with this on the next slide. So these are the events here where you would get an even or a payout of 0. So you notice these all add up to an even number, and there's 18 of these. And the total possibilities when you roll 2 die is 36. So half of the possibilities result in even. That's why you have a probability of x, our random variable, that's the event being even or odd, equaling 0. That has probability 1/2, and the probability of getting odd sum was the 2 die, is also 1/2, since there's 18 of the 36 possibilities being either even or odd. Okay, so the random variable is x. It has 2 possible values, 0 or 2, and then the probabilities assigned or associated with those 2 events are, in this case, 1/2 and 1/2. So slightly more formal than our sort of hand-waving definition on the previous slide. A random variable is a function. It maps the sample space S to a set of numbers y. The sample space is the set of all possible outcomes. A collection of outcomes in S is called an event. So in our dice example, the sample space was either even sum of the 2 die or an odd sum. So that's our S, and then it maps to either 0 when the sum was even or 2 when the sum was odd, just to put it into an example here. Then we have two quantities, which we'll get into. The expected value of X is sort of as the name suggests, the value you would expect, sort of the average or mean based on a formula. And then the variance is a measure of how much you vary from the mean. So you could have two random variables with the same expected value, but one may have a very large variance and another one may have a very tight, small variance circled around the expected value. So I assume you've seen these before, and that this is just kind of as a refresher to jog your memory. Here's the definition that gives this section, in this lesson, its name. A process is called stochastic if, when you observe it at different times, the outcome or state can be modeled as a random variable. The term random process means exactly the same thing, and you'll see both terms used in the literature. At each time you observe the process, there is a probability distribution over the possible outcomes. And in general, that distribution depends on what's happened in the past concerning the process. I have two different notations here for a random process or stochastic process. One is when we have a discrete process and it's labeled with an N. So there's a discrete number of processes or random variables, I should say. And at each time interval, the random variable x sub n can be in any one of these states. This is the state space listed here. And then for a continuous time random process, we use t instead of n. So t could be typically any positive number, 0 or larger. So each subscript is a different random variable. And the collection of random variables, that family of random variables, is what constitutes a stochastic process. Before I get to classifying stochastic processes, I want to talk a little bit about random walks, since I'll use those as examples in a few cases of the classification. So in a two-dimensional random walk, a transition can move more than one unit, and the directional probabilities do not have to be equal. A two-dimensional random walk is defined by its set of step vectors and their probabilities. And I have a few examples here. So from point xy, where you're in an xy axis and there's a point moving either up or down or left or right, you have some possible transitions here. These are just examples. So you can move from xy to x plus 2y, so that would be 2 units to the right, or you could go 1 unit to the left. You'd be going from here to here, or up 3 units. Y is the up and down. Or you could go diagonally, but that would involve going along the grid. So you would go you would go right 1 unit and down 2 units in this case here. The only basic requirement is that the transition probabilities sum to 1. So you could have drift, or you may not have drift. You could have balance. So you just think about it. If someone is starting at some point here, the basic question is, will they eventually come back to that, or will they drift off in one direction? And you can determine that by taking the expected value of the components of the random variable. That's what I'm showing here. You have a random variable, delta x, and it has these two components, small x and small y. And if the expected value of this is just the expected value of each component, if those two components have expected value 0, then the random walk has no drift. And such a walk is called unbiased or centered. That just means that the probability is, or the expectation is, you're going to come back to the where you started. Then I have an example here where you have a balance, but this is just in a two-dimensional, a one-dimensional random walk where you can only go left or right. And you can go right 2 units was probability 1/3, and left 1 unit was probability 2/3. And if you take the expected value of that, it's just 2 times 1/3 minus 1 times 2/3, and so the expected value is 0, and that means it's balanced or unbiased or centered. So in any one of those 3 terms. If we shifted the probabilities and we made it, say, 2/3 to go right and 1/3 to go left, then this would add up to what? 4/3 minus 1/3. It would add up to 1. And so that would have a bias going to the right in that case. Okay, this is not central to our classification on the next slide. It's more of an aside. So the main thing to remember is that for a random walk, whether it's 1-dimensional, 2-dimensional, even 3-dimensional, any step lengths are permitted. However, the probabilities in going from a particular point have to sum up to 1. Okay, so now let's look at the classification on the next slide. So there's 2 ways to classify stochastic processes. One is by time, whether or not the process follows discrete time, as we saw with the random walk, time 0, time 1, time 2, or continuous time, just like the time on your clock. And then the other dimension is the state space, whether it's discrete, that would include finite number of states or a countably infinite number, or whether it's a continuous state space. And I gave an example of each one of these combinations. Discrete state space, discrete time would be our random walk. To count the time is discrete. It's 0, time 1, time 2. And each one of those times you can take a discrete number of steps. However, if you were allowed to take steps that were not discrete, in other words, 1.5, 2 3/4 steps, and so forth, then but it's still at discrete times, then that would be an example in this box here. Then you can have discrete state space but continuous time. So think of a server checkout line at a supermarket. So the states would be the number of people in line. That could be 0, 1, 2, and so forth. And the time would run continuously. And then you can have continuous time and continuous state space. So for example, the amount of gold held by a country or an individual, that could go up or down, say in grams, could be any amount. And the time is just, like time on your clock. So that would be a positive, and that in this case it would be a positive real number. Okay, so those are the 4 categories. We're going to focus more on the discrete side of this, but there are theories that cover all 4 of these. I want to discuss another aspect of stochastic processes, and that's the Markovian property. And when you have the Markovian property for a process, the next state depends only on the current state. The path taken to getting to the current state is irrelevant. A walker, for example, steps left or right from where he stands or she stands now. This is the case we will develop in detail. So we'll focus on this. Then, and in the non-Markovian case, of course, it's not having this property. The next state depends on earlier states, so maybe several states going back into the past. History matters, not just the present. And going back to the random walk example, a walker whose next move is determined by where he was 2 steps ago or 3 steps ago, that would be non-Markovian. These are harder to analyze and largely outside the scope of what we're going to cover here. Okay, so a good example might be the stock market, where you have to look back more than just the current day to get even an idea of where things may be going. So that would be a non-Markovian process. Then we have a particular type of Markovian process. It's called a Markov chain. A discrete time, discrete state, space Markovian process is called the Markov chain. So if we restrict ourselves to discrete time and discrete state space in relative to a Markovian process, we have what's called a Markov chain. And I have it defined here in more detail. So let x sub n, this set here, be a sequence of random variables. So that's the related to this discrete time. N is the tracking the time. The state space I is finite or countably infinite. So that's the set shown down here. The subscripts on I labels the state. So this is state 0, state 1, state 2, and so on. They do not refer to the time. The time is n here. So for example, at time 2, you could be in state I sub 0. Why is this the case we're studying first? Well, discrete time and discrete states let us work with matrices and sums rather than differential equations. Everything can be computed by hand, which makes the ideas visible before we move to continuous time in part 9 or lesson number 9. So we're just in lesson 1 right now. Okay, so let's continue. There's actually a more formal way of stating this Markov chain property, which I'll show you on the next slide. So here I'm stating the property, the Markov property, a little bit more formally. It's a conditional probability. That's what this slash means here. So given where you were in state at time 0, at time 1, all the way up to time n, the probability given all this, and that at time n plus 1, you're in state I sub k n plus 1, is the same as the probability of just given the current state and going into this state I sub k sub n plus 1 at time n plus 1. In other words, all this past at time 0, 1, all the way up to n minus 1, that is not needed in order to do the computation. So this is essentially the Markov property. Then going back to words again, given the entire past history of the process, the transition to the next step, this step here, depends only on the present state. In other words, just where you are at time n and not all these other transitions beforehand. We have a couple more conditions related to Markov chains. The first one is called time homogeneous, and that says that the transition in going from state I to state j at from time n to time n plus 1 doesn't depend on n. It's the same probability. So whether you're going from I to j at time 1 to time 2 or from time 11 to time 12, the probability is always the same in going from state I to state j, independent of the time. So we don't put any n in the notation here. We just have Pij. Now this doesn't hold for all Markov chains, but for the ones we're studying, this will typically be true. Then we have another property that's always true, and that just says the probability of going from one state to another state, any other state in the state space in one step, when you add them all up, you get 1. In other words, you have to go somewhere when you transition. Now you could return to the same state, so that's also a possibility. And we've written this more formally here, so it's just saying the probability of going at time n and state I to at time n plus 1 to state j, when you sum over all the possible states, equals 1. And that's true for every Markov chain. Then we have another concept here called communicate. And that's pretty simple. It just says two states can communicate if each is reachable from the other. Reachable means by a sequence of transitions of positive probability. So we have an example here. We can go from 1 to 2. I didn't put in the probabilities on these lines here, but the implication is there's a positive probability of going from 1 to 2, or from 2 to 1, and same for 2 and 3, and 1 and 3. So these states can all communicate with each other. In one step, actually, they can communicate directly. And communication is an equivalence relationship, so it partitions the state space in the communicating classes. A chain is irreducible if there is exactly one class. So this would be irreducible. We can add a few more states in here just to make it more interesting. So now 1 and 5 can communicate. It's not direct, right? You have to go from 1 to 3, and from 3 to 4, from 4 to 5, but they can communicate. So that we're still having an irreducible chain. However, if I removed this line here, let me just cross it out. So let's say this wasn't here. Then you would have two communicating classes, 1, 2, and 3, and then 4 and 5. And you wouldn't have any way of getting between 4 and 3 if we remove this link here. This is the last slide in this lesson. So let's just do a quick summary. A stochastic process is a family of random variables indexed by time. Stochastic processes are classified by time, either discrete or continuous, or by state, either discrete or continuous also. The Markov property we mentioned, only the present state matters. So when if you're looking for the probability of going from one state to another from time n to n plus 1, you don't need to look at the states before time n. You don't need to look at the past history, basically. And then we just talked about time homogeneity, which is an extra property. It doesn't hold for every Markov chain, but the ones we're going to look at will typically have this property. And then the sum of the rows leaving a particular state has to add up to 1. It just says you have to go somewhere at each transition. So this is pretty almost self-evident. And then we have 11 more lessons, actually. The next lesson, part 2, we're going to cover these topics here, which I'll go over quickly. We'll talk about a transition matrix that has all the probabilities of going between the states. And then we'll talk about getting from one state to another in multiple steps and the probabilities of that. That's called the Chapman-Kolmogorov equations. And that'll actually be, once we have the matrix of going from one step to between the states, we can just raise that to a power, and we'll get these probabilities of going from one state to another in n steps. So we'll work through that. Then we'll talk about absolute probabilities when the starting state is itself uncertain. So you need to kind of know where you start in order to make use of these probability matrices. And then we'll do some worked examples related to random walks. Okay, so if you like this video, please remember to give it a thumbs up and stay tuned for the additional videos.